Okay, so the second lecture is, or the second chapter of topic 1 is about accuracy. So in real world, you can't actually get the exact value, right? You have to approximate. Example, your height, like not maybe your height is let's say 180. If your height is let's say 180, right? But I don't think it's going to be exactly 180. It could be 180 point or 180.01, 180.25, right? Maybe it could be 2526, 25268, just more accurate, right? You get more value, but whether it's accurate or not, that depends. But you get more values. Now, so in many instances in life, you have to approximate. So we talk about accuracy here and rounding up decimal places. So let's talk about rounding a number out. Rounding a number. Let's say you have 28,617 students, right? If you were to round it to the nearest 10,000, then this number would be reported as 30,000 because that's the value closest to the 10,000 value of the. I could report it as, let's say, if I want it to be the nearest 1,000, then it would be 29,000 because it's closest to the thousands place. And I could also report it as closest to 100. Rounding to the nearest 100 make the value 28,600 because that's the closest number to the 100. Now it's called rounding. But as you can see here, this is actually, when I round this part up, I rounded it up, but over here I rounded it down. And the reason being, when you're going to round the number nearest to 10,000, as you can see here, 10,000, you have to look at the value before it. Is it more than 5 or is it less than 5 or is it equal to 5? If it's more than 5 or equal to 5, right, you round up. If it's less than or equal to, if it's less than 5, you round down. As you can see here, 6, since this number is 1, which is obviously less than 5, so we round down. Okay, so the closest one is to this number is closest to 600 than 700. Whereas this number, say, if I were to round down, it would look like that. But since 28617 number over here, right, it's closer to this number than to that, so we round up. Now let's talk about approximation of decimal places. So let's go with this. Decimal places. So let's say I have 7.864. And if I want to round to the first decimal place, dp represent decimal place. If I want to round to the first decimal place, it would be 7.9. We look at somewhere the first decimal place, the second, the third, and so on. You'll get 7.9. The example is 5.574. If I were to round to 2 decimal place, to 2 decimal place, I would get 5.57. Okay, first decimal place, second decimal place, round to the close second decimal place. I would have to round down because it's 4. We use the same concept, use the same standard. We look at the number. If it's more than or equal to 5, we round up. If it's less than that, then we round down. Since 4 is less than 5, we round down. So let's talk about significant figures. Significant figures. A number can be approximated to a given number of significant figure. For example, let's say we have 43.25. Okay, and this number here, the 4, is the most significant figure to represent the most important value, the most significant, because the difference between 43.25 and 43.26, it's minimal, but the difference between 43.25 and 53.25 is huge. So it's the most significant figure, because the if you just change that value, it changed the value significantly. So that's the most significant figure. Now, if I want to round this to the third significant figure, right, it would be 43.3, because since it's the most significant, second, third, and it's the least, right? So to the third significant figure, and look at the number, it's 5, so we round up. 0.0043 is another example. If I were to round to the first significant figure, it would be 0.004, because this is the significant figure. This is not really a significant figure. Okay, it doesn't count. It's just the first one. It's here. Now, let's see. You could try approximating technique for an example. Let's say that 57 times 246. Let's say you don't have calculator, you just want to approximate it. But we know that 60. Let's round this up. 60 times by 200. Okay, we get what? That's easy. Now, let's round this thing down. Okay, and this thing will go up. Round one of them down. This is round down of this one. and this is the round up of that one. This is the round down of that one. And now we reverse the process. We round this one down and we round this one up, and you get what? So with this, we know that the numbers lies between these two numbers for sure. Okay, we could approximate using that. Another example is, let's say, approximating 120. Cube root of 120. So cube root is essentially asking for three numbers that are exactly the same, that when you multiply, you get that number. Okay. You could plug this into a calculator, but let's say you don't have a calculator, you just want an approximation. It doesn't have to be very accurate. Just a rough explanation, a rough estimation. So based on this, we know that cube root of 125 is equal to 5, right? Because 5 times 5 times 5, you get 5 times 5 times 5, you get 125. These are, and if you ask me how did I know this, it's something that you should remember. Like 1 power 3 is 1, 2 power 3 is 8, 3 power 3 is 27, and so on. It's something that you kind of remember. So root of 125 is 5, but since this value is less than that, so it should be less than 5, but hey, it's close enough, right? So it should be approximately 5. This is a notation for approximation. This is the equal. Okay. Now let's say you want to estimate a volume of something, right? And the dimension are given as, let's say 9 times 10.5. It can be any unit. Let's say it's called unit. Any unit, could be centimeter or meter. It doesn't really matter. And the height here is 2.2 unit. So let's say that I want to find the volume of this, right? But I don't want to do a complicated calculation like 10.5. I'm too lazy to do that, and you don't have a calculator. So you could say that, hey, you know what? It's at the minimum. At the minimum, it should be let's say 10.5 times 9 times by 2. That's at the minimum for sure. I could round this one down, right? So 9 times 2, you get 18. 18 times 10 plus 5. So 180 plus by 9, right? 189. Right, so the max value is probably, let's say, you round one of them up. Times by 11. So this would give you a value of 99 times 2.2. 99 times 2.2. Let's say well, let's approximate 99 times 2.2, since 100 times 2.2, you get 200 and 220, right? So by 2, so you get, this one is 218. that's just an approximation. So the range would be somewhere in between these two values, 189 and 218. That's okay. Let's talk about upper bound and lower bound. Upper bound and lower bound. So on a number line, say 4.5. Let's say we have a number 4.5, right? I can write 4.5 as 4.50 and write as 4.5000, right? But that's, you might say it's the same, but it's not true because you don't, it's the accuracy. It's only two significant, so I can't really write it as 2.50. Let's say you have something, let's say you measure a weight of something and you get 4.5 grams, okay? And you use another instrument that's more accurate. So that one might measure, like using instrument A, you get 4.5. Using instrument B, you get 4.56. Using instrument C, you get up to 4.561. Okay, get 4 significant figures of accuracy. So if I were to, let's say it's not 4.5, but it's 0.50. This is not the same. It might look the same because it might be, because in actuality it might be 4.501. Okay, so 4.5 is not actually 4.50. It's not accurate to say that. So there's like an upper bound and the lower bound for it. Let's say 4.5. If you were to round up, you will get 5, right? Round up, you get 5. Round down, okay, get 5. But if you were to round down, you get 4. Round up, round down. Right? But then, if you want a somewhat more accurate value, you could represent it this way using the upper bound and lower bound. So let's 4.5. The upper bound of 4.5 is 4. Okay. The upper bound of 4.5 is 4.55. The lower bound is 4.45. You look at this number here. So the upper bound is 0.55. The lower one is 0.45. And you could represent this using inequality. So let's say you don't know how accurate it is. It could be somewhere here or somewhere here. It could be 4.5, 4.501 or whatever, right? But you know it's in this range for sure. But you just want an accuracy of just 3 significant figures, then well, you could say that, hey, I don't know what to evaluate, but it lies in a range of this. Okay, it's could be 4.45 for sure, or it could be more than that. It could be exactly 4.45, but it could also be more than that, or it could be 4.53. Okay, but it cannot be 4.55 because that's the upper bound. Okay, that's the maximum value. Like, but it cannot be that. But this is the minimum. It can be this. So it'd be include from that value to somewhat before 4.55. Okay, so it could, the range is 4.4 up to 4.5, 4.54 or 4.544 or 4.5449. We are using 3 significant figures here. Okay, so let's say the example is, let's say we have a number 34. The lower bound of 34, lower bound LB, lower bound, okay, 33.5. Okay, we read this number, 33.5, and the upper bound is upper bound UB, representing upper bound is 34.5, an increase of 0.5, or increase or decrease of 0.5. The example is 65. The lower bound of 65 is 64.5. Look at this number, reduced by 0.5. The upper bound is 65.5, an increase of 0.5. Okay, and that would conclude the lecture for accuracy. But before that, let me introduce you to a few notation first. Few symbols and notation that's in maths. Now, this one represents equal. Okay. Over here, we have more than. This would be less than. A more than symbol with another short line segment is more than or equal to. So 4 is more than 3 for sure, right? But let's say 4 is more than or equal to some value. That value could be 3, could be 3.9, could be 3.999, could be 2.999, doesn't really matter. So any of these values satisfy, right? Oh, sorry, my bad. Any of these value would satisfy this condition right here. But for this one, it's not only restricted to 3.9999, but 4 is also fine because 4 is equal to 4. That's fine. But over here, this value has to be more than that, no matter what. So this is the notation. Another notation is you know about the division sign already, so I'm not going to talk about that. I'm going to talk about ratio instead. Ratio. Let's say you're in a classroom, and the number of students for male is, let's say, 24, and the number of female is, let's say, 30. It's 30. There's more females here. So I can write, hey, the ratio of male to the ratio of ratio of female. The ratio of female is 20 to 30, but well, that's not a complete answer. I could reduce it further. I want it to be like the lowest ratio. So I know they have 24 students for 30 students, but I want to know, hey, what's the ratio? What's the proper ratio? Like for, let's say, one student of this, or like for the ratio, I could reduce it, and let's say 24, I could reduce to 12, and this should be divided by how you get 15, right? So for every 12 students, there are 15 female students. For every 12 male students, there are 15 female students. So I could use what we learned in the first lecture, finding the highest common multiple to reduce it further. But since what we have here, we cannot reduce it. We can reduce it further into since 15 is equal to 5 times 3 and 12 is equal to 4 times 3. I could write as 12 students for every, oh, my bad, 4 students, 4 male students for every 5 female students, okay? So what I essentially did here is reducing it, divide by 2, divide by 3, I get 4 to 5. So that's the reduced one, like the smallest ratio I could represent is 4 to 5 for every 4 male students and 5 female students. So that's ratio. And it doesn't have to be just 2 variables. It could be, let's say you go to a market and you have apples and you have banana, and then you have kiwi, right? And the number of kiwi is, let's say they have 25, and they got 30 for banana, and they have, let's say they have 50 for apples. So if somebody asks you what's the ratio of these, of apples to banana to kiwi, right, the ratio, I could start with, I could start with 50 first, write 30 here and 25 here, and slowly reduce it. So since all of them have 5 as a common factor, I could divide 5 to all of them, and then this one have 10. And I could divide 30 by 5, I get 6. 35 by 5, I get 5. And that's the most reduced one. So the ratio of apples to banana to kiwi is 10 to 6 to 5. Okay, so that's the notation for ratio and what it's used for. And there are many more symbols that we won't be talking. Oh, and the other one is, since we have more than and more than equal to, we also have less than, just right here, and less than or equal to, which works the same way as the example that I showed earlier about more than or equal to, but just works the other way around. Okay, and that would conclude the second chapter of the topic 1 number accuracy and also the notation.